It's like just like doing acids, but now you're making hydroxides. So they found it relatively straightforward, and if anything, it's a good practice for what we did on Wednesday. Okay? All right, so first thing is that your book makes the approximation that in this example, when we had a strong acid and a weak acid, they basically just say whatever the stronger one is the one that's going to dominate. Okay? So if they were to do this problem, they would have just done that first step and said H3O plus is 0.1 because that's what's coming from the strong acid, and they would take the negative log and say the pH is 1. Okay? The amount that's contributed from the weak acid is small enough that it doesn't actually end up affecting it. There's also this thing called the common ion effect, which we're not going to do because it's at the end of chapter 18, which actually pushes the equilibrium for the weak acid because you made all this H3O plus from the strong acid. So you don't need to worry about that. The takeaway for the homework problems, write this down, is if you have a combination of two weak acids, only calculate pH based on the strongest acid. Not a strong acid, but the strongest one. So the larger K. So I saw things like when I looked at the example problems, things where you had a weak acid where it was 10 to the negative 4th and it was combined with another weak acid that was 10 to the negative 10th. You can just ignore the one that's 10 to the negative 10th. You can do the problem. If you did it the way we did it up here, where you did one and you did the other and you added them together, it actually wouldn't change the answer. So it's not like bad to do it that way, but it's not going to matter. So just ignore the weaker of the two and treat it like any other weak acid pH calculation. So, and because of that, we'll skip the last question in today's notes too. That's a combination of weak bases. The main reason I want to skip that one is because they're too close. Like the two KBs are really close. So this last slide, we're going to skip that. The KBs are 10 to the negative 4th and 10 to the negative 5th. So in that instance, it would make the calculation more difficult. There's not one like this on the homework. I'm not going to put it on the test, so we're just not going to do it. If we do have time at the end, I'll pull up a question that is like the two weak acids where the Kas are very different, and we'll just do that one for the sake of reinforcing how to do the homework problem.
There is something about if you only use an ice table if it's like strong acid as opposed to
weak, other way around.
Weak acid.
Yeah. If it's a strong acid, you do not have to do an ice table. And that leads in well to, we're going to do strong bases, which you also don't need to do an ice table because you know everything gets converted to products. So there wouldn't be a minus X, it's just all of it. So we'll do that here too. Okay, so reminders about bases. Sorry, I'm going to check my phone. My doggy is getting his teeth cleaned today, which if you don't know, they have to put them to sleep, like under sedation, like they're having surgery to have their teeth cleaned. So I'm going to like be aware of if there's a phone call or something. Can we pull your dog's tooth out or whatever it is? Okay. So strong bases are salts, so a metal with a hydroxide ion. Now, usually we think of them as just the 1A elements, so lithium, sodium, potassium, rubidium with a hydroxide. And these are the ones we talked about earlier. We called them type 1 bases. So that was where the hydroxide is part of it. The reason why hydroxide gets produced is because when it reacts with water, I don't even want to write the water in there, but when it reacts with water, it breaks down into lithium ions and hydroxide ions. And those hydroxide ions are what it makes it basic. And it does it all the way to completion, like all the way to products. And then the second set, these are the 2A elements. So this is like magnesium and calcium, that column. And when these guys break down, they actually produce 2 hydroxides because they've got 2 in the formula. Remember, that comes from the fact that in the second column, those are 2+ ions. And so when they mix with hydroxide, they need 2 of them. So this is the one instance of acids and bases where the coefficients aren't all 1. So for the example, let's just use strontium hydroxide. When that one breaks down, you're going to get strontium 2+ and 2 hydroxides. So when we're doing problems like this, you may want to think of it like stoichiometry, or just recognize if there's 2 of them, you're going to make twice as much. Like if I have 1 mole of strontium hydroxide, I'm going to make 2 moles of hydroxide ions when it dissolves. And we'll do a problem like that just to re-emphasize it, okay? And then the weak bases are the ones that are reacting with water and making hydroxide because the water acts as the acid and donates its proton. So then what's left behind is the hydroxide. So it's like 2 different methods for producing hydroxide. And the calculations with weak bases are going to be almost identical to the ones we did for weak acids. It's just that now the product is hydroxide instead of hydronium. So when you're doing a pH calculation, you're going to need to do 2 steps, right? Either solve for the POH and then get pH, or solve for the hydronium ion and get pH. But everything else will look almost identical. You'll use the Kb instead of the Ka since it's a base. All right, so let's jump into those sample problems. So first one here, lithium hydroxide, calculate the pH of this. I'm not going to give much of an introduction here and just let you guys take a look at it. Give you maybe 2 minutes to go through it. So you definitely don't have to write it out in this level of detail, but I'm just trying to emphasize why this is the case by showing you the steps. Okay, so again, the concentration of a strong base, you know now the concentration of the OH minus is the same as that. assuming that it's only one hydroxide in the formula. So all you need to do is look at it and say 0.18 molar lithium hydroxide. Okay, then the hydroxide is also 0.18 molar. Then to get to pH, you have to do the multiple steps, right? So you're going to take that, and so we can do OH minus to POH and then to pH, which is my preferred, or you could go to H3O plus and then to pH. Okay, so I'm gonna do the POH route, negative log of 0.18. So that gives me a POH of 0.74. So the pH should be 13.26. Which makes sense, pretty close to 14 because it's a strong base. All right, any clarifications on that? Okay, let's do the next one, which is 0.18 magnesium hydroxide. So slightly different here. Do 2 minutes on that one again as well. So it is actually reacting with water. It's just that we don't show the water because the water doesn't move the hydrogen. Like that happens independently. So it's not reacting with water, it's reacting in water, which is why we don't show it in the equation. Yeah, so I should write the equation for this one too, just so that you guys see. Again, it's a 2-to-1 ratio here. So like I said, this is the only one in acids and bases where you're gonna see a 2-to-1 ratio. Sorry. So you just need to make sure to multiply the original concentration by 2. You can think of it like a stoichiometry problem. It's 2-to-1, so there's 2 OHs produced for every one of the original base. So the POH here is 0.44, which means the pH is 13.66. So higher because we've got twice as much hydroxide coming from that. This is a good example of the fact that pH is a logarithmic scale, meaning that just because you double the OH minus, that doesn't mean the pH doubles, right? It goes up, by 0.4 in the pH scale, although it doubled the OH minus. That's kind of how, exponential or logarithmic scales work. Okay, so those are your two strong base examples. No ice table, just like we talked about before. You don't even have to write out the equation or stoichiometry. If it's a 1-to-1 ratio, it's just the same. If it's 1-to-2, multiply it by 2. Those are the only two variations. Okay, so weak base is next, which is where we're going to have to actually do an ice table here. So let's see, do I have 2 examples of this? No, I don't. Do I want to start you guys out? No, we have time. I'm going to let you work through it a little bit. Try to do as much on your own as you can. What I would say is refer back to one of the weak acids if you're like, how do we do this? Here, I know, I'll write the steps. So write the equation or the reaction. Set up an ice table. Use KB to solve for X, which will be equal to the hydroxide ion concentration, and then convert that to pH. Okay, I'll obviously give you longer on this one. Problem is, then it like dings me for every little thing instead of just, a phone call or a text message. Oh my gosh, I'm gonna lose my mind. Okay, so I'm getting you started with the reaction. So if you're lost, go from here and work through the ice table just like you did with acids. Okay, so I'm going to continue this on. Now, I'll say that more and more, we're only looking at things that have very small k's. So we did, the complicated ones in 16. Colton was kind of asking about this. How do these compare to chapter 16? Well, we already made you guys do ones that were more complicated math, that had quadratic formula, and so we kind of stopped putting that pressure on in these two chapters. So I don't know that we're going to have any more examples where we have to mess with the quadratic formula. So this one, same thing, 10 to the negative fifth. So we can ignore this minus x here. I've got to erase this to actually show you. So there's our completed ICE table. And the KB, we're going to set that equal to x squared over that original concentration, just like we've seen every single time now. The difference is that x is equal to OH minus rather than H3O plus. So then we're going to take that and convert it to pH. So this is where we're back to that, the four things with the arrows and all of those equations. That's why, hopefully you did enough of those that you're comfortable with them, because now we're doing them in context of another problem. So I'm going to do POH for this. So negative log of 2.55 times 10 to the negative third. So the POH is 2.59. 2.55. Did anybody else get that? 2.55 times 10 to the negative third? Okay, just want to check. Sometimes I'll remember what we did last class and I'm like, I don't remember that same number coming up. Okay, so then the pH in this case is 11.41.
I guess the question really is, why did the ICE tables for acid-base come out nicer than the equilibriums in 16?
Because they're 1-to-1, because all of the equations, the coefficients are 1. So you never have plus 2x. Yeah. And we haven't seen any yet where these initial concentrations are anything other than 0. So we've only said the initial amount of the base. Now in 18, that's where we're going to add amounts on the top, because we're going to be dealing with buffers. And a buffer is where you have an acid and its conjugate base mixed together. And so we'll have initial amounts on both of the top ones.
Now I'm starting to understand why it made such a headache.
Yeah, because there were different amounts, there were coefficients. We did a lot where you couldn't ignore the K, like if it was 10 to the negative second or something. Yeah. All right, so the next thing we need to talk about is the relationship between the acid conjugate base pairs. Maybe as a review, let's look at this equation up here, the NH3 one. So in this equation, we would say NH3 is the base, and NH4 plus, the thing it turns into, is the conjugate acid. And we would consider those to be a pair, because they're basically the same molecule, just differing by that H plus that got either donated or accepted. And then the water and the OH minus would then be the acid and the conjugate base. Now, we don't usually think about those ones as much in the larger context because they're there all the time. Anytime you have a base, you're going to have water acting as the acid. So good reminder of the terminology, because now we need to talk about the relationship between the Kb of the base and the Ka of its conjugate acid. So these two things, the NH3 and the NH4 plus, are kind of in competition as to which one is more likely to either accept the proton or the acid to donate it, right? Because that's comparing the forward reaction here with the reverse reaction. And the connection between those two things comes from the Kw. So I'm not going to show you all the work of why this works out, but just trust me that if we look at the Ka times the Kb, so this would be the Kb for the conjugate base of a particular acid or vice versa. So in this example, it was NH3 and NH4 plus. So the Ka of one and the Kb of the other, when they're a pair, is going to be, when you multiply them, it will be equal to the Kw, which is that 1 times 10 to the negative 14th. Which basically just means if you know information about one of them, like Kas are very often reported, Kbs are not, simply because you can calculate them from the Ka. So usually when you see tables of things, you'll see tables of Ka values because they know that you can determine the Kb of the conjugate base by calculating it through this. Okay? The other relationship is we can put it in the log form and do a pKa and a pKb, just like with pH and pOH, and those would be equal to 14. So I don't use this quite as much, but you know, it is useful in some instances. Certain industries will tabulate pKa values or talk about them a lot more than just Kas. Again, because it's like pH, it's a little bit easier to communicate, you know, oh, its pKa is, you know, 10.4 rather than like 1.87 times 10 to the negative whatever, 11th. Okay, so let's look at an example of this with the NH3. So the NH3, the Kb was 1.76 times 10 to the negative 5th. So I'm going to write that down here, 1.76 times 10 to the negative 5th. Okay, so let's go ahead and calculate the Ka for NH4 plus using this. So Ka times Kb is equal to Kw, which is 1 times 10 to the negative 14th. Okay, so Ka then would be 1 times 10 to the negative 14th over 1.76 times 10 to the negative 5th. So that comes out to give us a Ka for NH4 plus of 5.68 times 10 to the negative 10th. So I'm going to write that over here, 5.68 times 10 to the negative 10th. Okay, so both of these guys fall into the weak category, right? NH4 plus is a weak acid and NH3 is a weak base. But just by looking at their Ks, the one that's larger, the Kb, that tells us that NH3 is better at being a base than NH4 is at being an acid. So if we look at the equation above, this one, we can kind of think of these two in competition. And in this case, the NH3 is going to win, and there's going to be you know, you could even say if you stuck both of these in equal amounts in solution, it would be basic because the base is going to dominate simply because the KB is higher than the KA. Now, the other thing I want to do, and I think I'll just look up what the, let's see, the KA will do HF. So HF, a little further up, this is 6.8 times 10 to the negative fourth. So go ahead on your own and calculate the KB then of F minus, and then I would compare HF with NH4. All right, so check your answer on that. So the KB of F minus 1.47 times 10 to the negative 11. So you see this interesting trend that we're looking at. So this, let me back out so you can see the arrow. Okay. This is acid strength on the acid side. Top is the strongest and they get weaker and weaker as it's listed. And you can see that here because this is a bigger K than that, right? So HF is stronger and then you're going down to weaker acids. What happens is the conjugate base of that acid ends up being stronger the weaker the acid is. Again, because they're kind of like in competition with each other. So on the NH3 side, this is not strong, but it's stronger than that conjugate base. Okay? So the stronger the acid, the weaker the conjugate base. And as the acid gets weaker, the conjugate base gets stronger. Which, if you think of a strong acid, this should make a lot of sense. If you have HCl and water, and it reacts to form H3O plus and Cl minus, how likely is it that that Cl minus is going to turn back around and turn into HCl? It's not at all going to happen. That's why we have the one arrow going that one direction, because it's not, Cl minus is a terrible base. This is technically the conjugate base, but it's really bad at acting as a base. Okay, that's the vet, so I'm going to answer this phone call in the middle of class. This is Carrie. Hi, yes. Just fine, thanks. Yes. Great. Oh, okay. Okay, perfect. I finished teaching at noon, so I'll come by and get him after that. Great. Oh, good. Okay, terrific. Okay, thanks so much. Bye. I didn't have dogs as a kid, and it was always like, oh my gosh, people are so obsessed with their dogs. They treat them like their children. And she's like, oh, he's such a good dog. He's such a good dog. And I'm glowing like a parent glows about hearing their kids are such good kids. And I have 3 kids. But yeah, dogs kind of do become like little babies. Okay, so let's do one more problem. I should have had you guys start working on this while I was talking. Okay, we're going to do one more practice problem and then we'll be done for today. So this is a base again, but you're given the Ka. And then the other thing that's a little bit different is I actually ask you for all 4 of those quantities rather than just one of them. Okay, so same approach as any other base problem. You'll just have to calculate the Kb in this instance.
Was the CL, was that a minus?
Yeah,
Or-
yeah. Oh, yeah, it is kind of covered up.
Yeah. That was one.
Yeah. So summarizing on that, since I kind of, cut into the very end there.
Yeah.
The stronger the base is, the weaker that the stronger the acid is, the weaker that conjugate base, meaning it's not going to act as a base. Like in a strong acid, the conjugate base will not turn around and go back into HCl.
So H2O is an acid in that too, right?
No, because you always have an acid and a base. So this is your acid and this is your base. Because if you look at it, the hydrogen is given to the water. And so the base is accepting the H+, and that's what bases do. They're H+ acceptors.
I see the difference now.
So this last part here is just practicing those different quantities that are all tied together. So hopefully this feels pretty doable since it's really similar to the Wednesday stuff. Homework for, this is the end of 17. Homework for 17 due on Sunday. And then we'll do 18 all next week, 3 days. We're only doing half of the chapter, but we should have a decent amount of time since it's 3 days instead of normally we spend 4. And then that'll be due on Sunday as well. And then the exams the following week after that. And then it's done. Okay, have a good weekend.